Okay. Hello, everybody. My name is Daoyong Cong from University of Science and Technology, Beijing. Uh, First, I would like to thank Professor Shenenko for inviting me to join this conference. From the online conference, I also see several friends, including Professor Luis Manessa and others. I changed my topic a little bit, which is now exploration of magnetic sheet memory alloys for caloric cooling. We know that the magnetic sheet memory alloys show magnetic field-induced transformation. Magnetic transformation in this kind of alloys can be driven by temperature change, stress, or magnetic field, which give rise to a lot of multifunctional properties, including superelasticity, sheet memory effect, magnetic field-induced strain, magnetocaloric effect, elastocaloric effect. Because this phase transition can be driven by multiple fields, so multi-caloric effect is possible to be achieved under the coupling of multiple external fields. However, these kind of alloys are very brittle, and the critical field for magnetic field-induced transition is too high, which are two bottlenecks for applications. Another disadvantage of this kind of alloy is that its elastocaloric effect is small, especially when we compare it with nickel titanium. Our recent work mainly focuses on 2 points. The first one is overcoming the brittleness issue, for which we use a strategy of forming oligocrystalline structure through microwire preparation. And the second part is high performance design, and we have got elastocaloric effect with adiabatic temperature change as high as 31.5 Kelvin. The first part is more related to neutrality, and the second part is more related to physics. So now the first part, overcoming the brittleness issue. We know that nickel manganese-based magnetic sheet memory alloys show multifunctional properties, including magnetocaloric effect, elastocaloric effect, and paracaloric effect. And it can realize multi-caloric cooling under the coupling of multiple external fields. But the polycrystals are very brittle, the grain boundaries are very weak, and they are prone to intergranular fracture during loading. Therefore, the cyclic stability of the elastocaloric effect is very poor, which hinders its practical applications. Our strategy is to create this kind of oligocrystalline structure through microwire preparation. With this kind of structure, we can increase the surface area and form a bamboo-like structure. We know that in polycrystals of magnetic sheet memory alloys, during the phase transformation, there is strain incompatibility at triple junctions or along the grain boundaries. So it is very easy to form stress concentrations at the triple junctions and the grain boundaries, and thus during loading, cracks can easily occur along the grain boundaries or at triple junctions, leading to a brittle intergranular fracture. But with this kind of oligocrystalline structure, because the surface area is large, there are only a few grains in the sample, and it has bamboo-like grains. Therefore, we can reduce the strain incompatibility at grain boundaries during both deformation and stress-induced phase transformation. This allows the transformation and deformation to occur in a much less constrained environment. And therefore, the intergranular fracture can be suppressed, and the mechanical properties can be improved. So we first use arc melting to prepare the button ingots, and then we use suction casting to get the cylindrical rod. And then we use this Taylor method to bore wires, and the wires can have a diameter between 20 and 300 micrometers. And the micro wires can be several hundreds of millimeters long, and it has a smooth surface, a uniform diameter. And we first tested composition with nickel, copper, cobalt, manganese, and indium. And this microwire shows sharp transformation peaks. And also we can detect the Curie temperature in the DSC curve. We see that there's a large difference between this Curie temperature and this transformation temperature. This is quite beneficial for magnetic field-induced transition. First, we studied the crystal structure at both high temperature and low temperature by and the X-ray diffraction experiment. We find that the austenite has a B2 or L2 and hot structure, and the martensite has a monoclinic 6-layered modulated structure. Then we investigated the mechanical properties and superelasticity. We know that for the bulk polycrystals or magnetic sheath memory alloys, it shows hardly any tensile deformability. Even for compression, the superelastic strain is usually small, about 1%. But for the microwire, we get very large tensile superelasticity. The recovered strain can be more than 10%. And also, the strain can be fully recovered after unloading, giving rise to a perfect tensile superelasticity. We checked the fracture surface of the bulk sample. We see that it's intergranular fracture. For the microwire, the fracture mode is mostly transgranular fracture. This means the grain boundary in the microwire is not the weak point anymore. The fracture occurs inside the grain interiors in the microwire. And we checked the superelasticity at different temperatures. We find that we can get perfect tensile superelasticity at temperatures from 253 to 313 Kelvin, with a large recovered strain more than 5%. And also the nucleation stress and the propagation stress increases with the temperature. Then we want to check whether there's magnetic field-induced transformation in the microwire. We first performed thermomagnetization curves. We find that apply a magnetic field significantly increases the phase transition temperature. Therefore, it is possible to induce transformation with the magnetic field at constant temperatures around the phase transition. Then we check the magnetization as a function of field. We find that at different temperatures between 166 and 180, we have a strong magnetic field-induced first-order phase transition. Although this transition is somewhat irreversible during the first cycle, starting from the second cycle, it becomes fully reversible. This reversible magnetic field-induced phase transition can give rise to a variety of magneto-responsive properties. For example, magnetochloric effect, magnetic superelasticity, magneto-resistance, and magnetothermal conductivity. We estimated the magnetic entropy change with this equation. We find that under a field of 5 Tesla, we can get a large reversible magnetic field-induced isothermal entropy change of 12.6 per kilogram per Kelvin. Just as we mentioned, we get both stress-induced transformation and magnetic field-induced transformation in the microwire. This provides opportunities for controlling the phase transition and optimizing the multifunctional properties under the coupling of multiple external fields, that is, magnetic field, stress, and temperature. With this part, I give a summary. We have developed an oligocrystalline microwire with both tensile superelasticity and magnetic field-induced first-order phase transition. This microwire shows perfect tensile superelasticity with a recovered strain more than 10%. This is in sharp contrast with the bulk sample that shows hardly any tensile deformability. A magnetic field-induced transition from martensite to austenite has been realized in the microwire, which may give rise to a variety of multifunctional properties. With stress-induced transmission and magnetic field-induced transmission in this microwire, we can try to get the multi-caloric effect under both stress and temperature. The second part is high-performance design for the big elastocaloric effect. This part of the work is done in collaboration with Professor Luis Manazza and Professor Anthony Planis. Our material design concept for getting a large elastocaloric effect mainly consists of the following 2 points. First, the material should have a large transition entropy change. This will ensure that we have a potential to obtaining a large elastocaloric effect. Second, the material must have good mechanical properties, so that when we have the stress-induced magnetic transmission, the sample will not break and will not deform plastically, so that the stress-induced transmission can be complete and we can make full use of the large transition entropy change. Know that for chip memory alloys, transformation entropy change mainly consists of 3 parts: lattice entropy change, magnetic entropy change, and electronic entropy change. Among these, the lattice entropy change plays a dominant role. Especially for magnetic transformation, the larger the unit cell volume change across the phase transition, the stronger the first. Our material design concept mainly consists of 2 points. First, the material should have a large transition entropy change. This will ensure potential for obtaining a large elastocaloric effect. The second point is the material should have good mechanical properties, so that during the stress-induced transition, the sample will not break and will not deform permanently. This will ensure a complete stress-induced magnetic transmission, which will make full use of the potential to obtaining a large elastocaloric effect. As we know that for chip memory alloys, the transformation entropy change consists of 3 parts: lattice entropy change, magnetic entropy change, and electronic entropy change, among which the lattice entropy change plays a dominant role. Especially for magnetic transmission, the larger the unit cell volume change across transition, the stronger the first order transition, and the larger the lattice entropy change. Therefore, this problem becomes we seek materials with both large volume change and good mechanical properties in order to get a large elastocaloric effect. Considering that the nickel-manganese alloy has a large unit cell volume change, we mainly focus on the nickel-manganese gas-based Hausler alloy families, which include nickel-manganese gallium, nickel-manganese indium, nickel-manganese tin, nickel-manganese titanium. We first use this first principles calculation to get the elastic constants and moduli. Focus on the parameters reflecting the intrinsic brittle or ductile properties of metals. They are B or G and C12 minus C44, which is also called positive pressure. We find that among this nickel-manganese-based alloy system, the nickel-manganese titanium has both the largest B over D and the largest positive pressure. Therefore, it is most probable that the best mechanical properties in the nickel-manganese titanium family. Thus, we prepared a series of nickel-manganese titanium alloys with the titanium substituting manganese. We find that with the increasing amount of titanium, the phase transition temperature decreases. Because we want to get the elastocaloric effect at room temperature, we mainly focus on the alloys with transition temperature slightly below room temperature. As I just mentioned, the nickel-manganese titanium alloy system has the best intrinsic mechanical properties. But for the polycrystals, we know that for this kind of polycrystals, especially for the alloys with large volume change across phase transition, the grain boundaries are very weak. Therefore, we use the boron microalloying to strengthen the grain boundary in this alloy system, so that we can expect that we can have good mechanical properties in the polycrystals. We used in situ synchrotron high energy X-ray diffraction experiment to get the unit cell volume change, which is as large as 1.9%. And we find S curve that transition entropy change is as high as 76. Therefore, we expect that we can get large elastochloric effect in this sample. When we tested the elastochloric effect, surprisingly, we find that during unloading, we can get a diabatic temperature change as high as 31.5 Kelvin. We also estimated the stress-induced isothermal entropy change by integrating the areas on the stress strain curves measured at different temperatures. We find that the stress-induced isothermal entropy change is up to 45 joule per kilogram per kg. We use in situ synchrotron high-energy X-ray diffraction experiment to trace the crystal structure evolution during loading. These are the diffracting patterns at different stress levels. We find that before loading, it is in the austenite state with the L2N Hausdorff factor with this lattice parameter. And after loading, it becomes martenstic. It has orthorhombic structure with this group and this lattice parameter. We carefully analyze the X-ray diffraction pattern. We find that at 413 megapascal, the stress-induced martensite is complete with no residual austenite. We checked the two-dimensional diffraction patterns before loading at the maximum stress and after unloading. We find that the diffraction pattern before loading and after unloading are almost identical. This shows that the stress-induced martensite transformation is fully reversible. The completeness and reversibility of the stress-induced martensite transformation is very important for the large reversible elastochloric effect. If the transformation is not complete, we cannot make full use of the lattice head. If the transformation is not reversible, the elastochloric effect can only be used once, not for repeated times. With the lattice parameters of austenite and martensite, we get a large unit cell volume change of 1.9%. This leads to a large lattice entropy change and thus a large transition entropy change. And finally, we get a large elastochloric effect. Now we compare the elastochloric effect in our material with other elastochloric materials. In our nickel magnetic titanium alloy with spark polycrystal, we can get a adiabatic temperature 31.5 Kelvin and isothermal entropy change of 45. In the nickel titanium alloys, even for the small size thin film wires, the maximum adiabatic temperature change is 25 Kelvin. The maximum isothermal entropy change is 35. For the bulk sample, no matter it's single crystal or polycrystal, the maximum temperature change is 15 Kelvin. We also compared with other materials, and we find that our sample shows the best elastochloric performance among all elastochloric materials, no matter whether it is in bulk, wire, thin film forms or in other forms. We also compared the temperature change with other chloric materials, including magnetochloric, electrochloric, and parachloric materials. It should be mentioned that here we only compare the adiabatic temperature change that is directly experimentally measured. We did not consider the values obtained indirectly or quasi-directly. And this is the position of our adiabatic temperature change, and we find that it is the highest adiabatic temperature change among all chloric materials. This is a summary of this part. We obtained a large elastochloric effect with an adiabatic temperature change as high as 31.5 Kelvin in nickel magnetic titanium alloy, which simultaneously has a large unit cell volume change across phase transition and good mechanical properties. With this, I want to thank the group members in my group who contributed a lot to this work. Okay, thank you very much for your attention.
Hi, Daoyong. Nice to see you on distance. I have just one question is about your micro wires, that there is a large difference between what you call the nucleation stress and the propagation stress.
Yeah,
Yes.
it's a
Yeah. So
huge tooth.
yeah. Do you have an explanation for such a large difference?
I think in this kind of microwire, when you want to nucleate a multisite, its entry barrier is very large. You need large stress to nucleate a multisite. Once it's nucleated, you don't need such a large stress, and it can propagate very easily. This may be because in the microwire we don't have many grain boundaries, and the microstructure is homogeneous. So there are quite few defects which can facilitate the nucleation.
Yeah. Okay.
I guess.
Yeah. I think. And do you think it could be a good strategy just to put some kind of defects or whatever in order just to reduce the nucleation barrier, but still keep just the good mechanical properties? So that would make even easier actuation for these micro wires. Do you think? I'm just guessing if it would be possible to put some nucleation sites somehow. I don't know if this is possible.
Yeah, yes, maybe it's possible because you see in the nickel titanium wires, in the nickel rich sample, you can introduce very fine precipitates, nickel 4, titanium 3. Maybe in this kind of material, we can try also to introduce some precipitates. Then we can reduce the barrier for nucleation on multisite without sacrificing the mechanical properties. I hope so.
Thank you.
Thank you.
Any other questions? I have a small question. In the second part, you get this data in the compression test, correct? You just
yes.
So what about do you have option to prepare the wires of this nickel manganese titanium boron and make tensile? Is it possible?
Yes. We tried. We devoted a lot of efforts to do that. Unfortunately, because it contains titanium, which is very active element, it reacts with glass. Because we use glass coating method, it reacts with the glass, and finally we didn't succeed to acquire this sample.
So it is not easy to prepare samples for tensile measurements. Not easy, no?
No.
Still,
because of the titanium here.
Still, it is not very ductile, like nickel titanium.
No.
So for the moment.
But for compression, we can succeed 5,000 cycle or
Yes,
even 10,000 cycle.
Yeah. Thank you.